Right, hello and welcome to yet another revision stream. Okay, I think I've done it so that if I write... gonna have to do it in reverse. Bollocks. Okay, that's annoying. I'm gonna flippity boot my camera around once again. Then flip, alright. Oh, that's literally did it perfectly. Okay. Right. Guess I should pull out my computer then so we can actually read chat. So, today I'm going to be doing more biology stuff. But this time, so last time what we did was I did some exam questions for about an hour. I remembered some important stuff, so that was all good, all helpful. But today we'll just do a big overview of the biological molecules topic and the cell biology topic. Because both of those topics are very useful. Well, they're basically like the founding blocks, the foundations. If I know them, then I know everything else. I'm just going to log in. What? Okay, YouTube, really? I was showing people the screen. My first thing in my recommendation is meet Russian women online. Thank you, YouTube. Thank you, YouTube, for giving me, like, the least dodgy ads ever. Ew. I wonder if you guys could see that there. I'm gonna move the camera ever so slightly. Right. We're good to go. So, yep, that's literally perfect. Okay. So, we're gonna start off. We'll start off with the cell biology topic because that's my favorite one to do. So we were learning about mitosis. So I always use the acronym. I prepare meals at the college, but we actually did a little bit more. So interphase is not really mitosis. This is mitosis. Prepare meals at the college, I guess. There are actually three major parts of interphase. So you have, pretty sure it's the first one, the ones and two. So during the first part, that is where all the organelles are replicated. This is the synthesis. The synthesis phase, or basically DNA synthesis. That's where the DNA is replicated. And during this second part, this is where it is checked and repaired. Now, what that basically means in summary is if a cell accidentally, I guess, messes up and there's an incorrect number of organelles or DNA, this will basically correct it. I'm gonna lift the camera just a slight bit up there. Is that fine? Oh, that's perfect. All right. So yeah, it basically checks it. Now, obviously, mistakes still can get through, but that's why things like cancer still occur, I guess. But for the most part, that is it. So that's interphase. And if we get like a pie chart, so this is going to be a very goofy pie chart, we see that mitosis only really takes up this amount of time. Interphase takes up a vast majority of it, which makes sense, because if a cell spent its whole time dividing, I mean, that would be pretty cool, maybe? I was saying to Ellis, if you get, like, stabbed, that'd be cool, because then it'd just instantly heal up, but you'd probably develop, like, cancer within a day, so Yeah, it's good that our cells don't rapidly divide. So we have prophase, metaphase, anaphase, telophase, and cytokinesis. Because yes, everything else is called phase. This one is called cytokinesis for some goofy reason. Why not call it cytophase? I don't know. Anyways, so now I'll be honest, we've just learnt this, and it goes against a lot of what I was doing in my revision streams. Actually, it changes quite a lot of things. So prophase is where you can imagine if we have a cell here, the nucleus is all messed up. It's like spaghetti, basically. That's because your DNA synthesis has caused, the DNA to basically replicate. So during metaphase, the DNA coils, and now it's obviously like strands. And then during anaphase, that is where I'm pretty sure the nuclear membrane breaks down, and where hang on, I think I've got this not in the wrong order, but the wrong matching up to the phases. Let me just check them a bit. Let me just have a look. Aha! No, I basically, prophase is where the DNA goes from spaghetti to strands. So where the DNA basically arranges, and then metaphase, that is the one where the nuclear membrane breaks down. Then anaphase is where they line up at the cell's equator, and where the centrioles are at the poles, and obviously they send out the spindle fibers, and then that's basically it, really. I mean, yeah, the cytoplasm divides, and the cell membrane, I guess, just separates them out, and then, yeah, a brand new nuclear membrane is formed around the genetic material. So, yeah, here, I kind of put it in more simple terms in my book, to be fair. So the organelles replicate, that's what we said here. DNA replicates. The cells are checked. Then the spindle fibers form. So we didn't actually mention that, but the spindle fibers begin to form during prophase. The cell condenses the chromosomes, so it doesn't tangle them or whatever, it condenses. So it condenses all the DNA into chromosomes. Then during metaphase, the spindle fibers are at the poles. So at that point, the spindle fibers are already at the poles. And the chromosomes line up at the equator. And then the spindle fibers are sent out, the DNA is pulled apart. Then the nuclear membrane forms again during telophase. So actually, I got those in the wrong order there. The nuclear membrane is back again. And then during cytokinesis, that is where the cytoplasm divides and the membrane forms. So, to be fair, it's like 50%. Did you? Yeah, I got your message. I tried replying. I don't know if you saw it, but because my internet's been a little bit weird. But yeah, it's weird. I've been able to figure out as well. My only lesson on Wednesday, is period 1. So I can actually do my period 1 lesson and then just go, like, on holiday. I will obviously miss form, but I've emailed the teacher, so I'm hoping he'll be able to sort it out now, so that it only counts as 1 day off. Maybe they misinterpreted what I was saying and they thought I wanted like a week off or something. Cause I don't know, bro. Anyways, so yeah, but basically this is like what I was saying on the revision streams. How, you know, except I guess we didn't get as much information. Like, I didn't know that the centrioles are what sent out the spindle fibers. So this is a more refined version of what we were doing during the revision streams, and I ought to add this to the biology document, which I'll do now, actually. If you guys give me like a minute, I'll update the biology revision document. And that will just help a lot. I see I haven't added anything about self-fractionation yet, which we'll move on to. So, prepare meals at the college. See, it's a good acronym. It's also telophase, not telophase. Teller, not teller. So I've been writing that wrong for the last 3 years. Oopsie. Goodbye. Bye, mint. Prophase. So prophase is where spindle fibers begin to form. DNA condenses into chromosomes. Metaphase is where So, there we go. It's honestly a very crude, representation here. I basically put the basic ass information from my book. I don't even know if you guys can see this. Oh god, I just dropped a shit ton of exam stuff. Oopsie. Let's go check chat. I don't know. Yeah, Luke Kelly hasn't said anything. So, anyways, is there anything else? No, that's basically it. So, we obviously have meiosis, which we should quickly mention. So that is for, is it gametes? That's I always forget that word. It's for gametes or sex cells, basically. So it's half as many chromosomes in each one. And what she mentioned, which I knew, that she'll probably mention in like another couple of months or something in lesson, is how genetic variation occurs. So it basically scrambles up all of the genetic information. It's like the cells pair together, they split off and stuff. And I remembered that. So yeah, it's for sex cells, half as many chromosomes, and the function of mitosis is to replace worn-out cells or dead cells. So it's for growth, repair, and to replace dead cells. And that's basically everything, I think. Oh, haploid and diploid. So diploid is the full number of chromosomes. Haploid is half. You can just kind of infer that because it says hap is in half, dip is in 2, I guess. So, you know. So yeah, that's basically that for the cell cycle. Now, cell fractionation is an interesting one. That is basically, and I'll go change like pens and stuff for this one because it's an interesting one. So cell fractionation. So this is basically where you would get tissue, add it to, I guess, like a beaker or something, and you would homogenize it. So if we get like, I don't know, I'm going to draw like a very crude drawing here. So you would homogenize this, and then you're left with your homogenate. Now, one important thing to do during this is you would use an ice-cold buffer solution. And it needs to, so this solution, what it needs to do is it needs to be cold. Basically, that is to slow down enzyme activity, to stop destructive enzymes, because what you're then going to do is you're going to use centrifugation. And what this does is it basically spins it around a bunch, and it separates out the heavy organelles from the light ones in a pellet. A pellet rich with a specific organelle. Now, using inference, you can kind of infer that the nucleus is going to be the most heavy, so that's going to obviously be at the bottom first, and then you would obviously filter it out, and then you would get, I believe, mitochondria, then I guess chloroplasts, and then etc. Then I guess ribosomes would be last. An important step to remember is to filter it out so that you get all the excess debris out before you put your homogenate into the centrifugation. And then that's basically that. That's the whole thing. So you would use an ice-cold buffer solution. Buffer keeps the pH neutral. It needs to be a solution with a no water potential, I'm pretty sure, or a constant water potential. What that means is that there is no net osmosis. Water doesn't leave or enter the cell, so the cell doesn't become shrunk or swollen, basically. But yeah, that's the whole thing. That is cell fractionation. That's a method you can probably get a question for a required practical on it, because it's very easy to understand. You could have to explain. I mean, look, we'll go through one or two of the possible exam questions now. Even I'm feeling generous today. Okay, how long have we been live for? Not even 20 minutes. We'll go for 40. We'll go for 40 today. So, filter. Why would you filter? Obviously, that is to keep debris out. Debris basically being, I don't know. So if we got a plant and we mashed it up or whatever, homogenized it, there might be a little bit of stalk that we don't want. So you would basically filter out the debris using filter funnel and a gauze. You homogenate, that's what it's called. I don't recall the exact word for the centrifugation solution. Let me find that now. A supernatant. Supernatant. That's what it's called. Now, I said heaviest, I meant densest. The densest organelles are the ones that are filtered first, and you need to spin it at different concentrations. Different frequencies. So, to begin with, you'd spin it still fast, so that it all the densest go to the bottom. But as time goes on, if you want to get to those really small organelles, you would need to spin it very quickly for a long time. So yeah, that is basically that. That's how you would be able to filter out and look at specific organelles. Very interesting. Now we'll do some microscope stuff. I obviously have a microscope and I did not know any of this, so pay attention. So, magnification. I'll just put MG. Magnification. I always get this definition wrong because it seems so obvious, yet it's not. It is how, I guess, zoomed in or how magnified an object is compared to how it usually looks. But let me go quickly find a proper definition there. How much an image has been enlarged by. That is a basic definition, but that works for everything. So how enlarged an image is. Or how an image has been, how much an image has been enlarged by. That's literally the definition, and I always get it wrong, and yet it is so easy. The buffer solution isotonic, that's the word I was looking for. That basically means the water potential is constant, so yeah, no net osmosis. So that is magnification. Resolution, I believe, is how much you can I always get these definitions wrong, guys. Only because they're so basic that it's hard to explain. Yeah, it's a clearer image. So how clear an image is. So higher resolution means your image is clearer. I mean, it makes sense for video games and stuff. If you have a low resolution TV or some shit, you're going to play God of War Ragnarok and it's going to look like you're playing a PlayStation 1 game. Higher resolution means a clearer image, alright? Those are some basic definitions that I get wrong. And the reason I get them wrong is, again, they're just so basic. It's so basic. It feels like you should know these, but it is so easy to just forget them. And in an exam, you could easily slip up and put the magnification as how big something is, or how magnified something is. Or you could put resolution as how, I guess, good an image is. You could mess up easily. Now, the fine focus moves the stage. So I'll put fine focus. That actually moves, so I guess if we draw a very crude microscope with our, I guess, objective lens there, it moves the stage. That's what it does. It literally moves the stage closer to the objective lens, and the rough focus literally just focuses. That's all it does. Now, the light microscopes have roughly, so we'll do light microscopes have a 400, I think, is it nanometer? Yeah, 400 nanometer resolution, so they can see up to 400. Now, if anything is basically smaller, because, okay, the way a light microscope works is light is shined through the specimen, so light is shined through, I guess if this is a specimen, a light is shined through there, and it's redirected through the actual eyepiece into our eye. Okay? So if an object is smaller than the wavelength of light, obviously it's not going to be, I guess, directed into our eye, is it? So light microscopes blur if it is smaller than the wavelength of light. And that's where electron microscopes come in. Electron microscopes are divided into scanning and transmission. Now, scanning, you have to think of it like a printer in a way. It builds a 3D image because electrons basically hit it. I don't think they go through it. They just hit it, and they're able to, I guess, use that to build up a 3D image. But it has a lower resolution of, I think, 4 nanometers. Oh, 20. So even worse than I said. 20 nanometers. A transmission, on the other hand, so, okay, we can explain this better. Beams of electrons are sent from above, and they are scattered. And what this does is it builds a 3D image of the electron pattern, because I guess an electron detector detects it, and it creates, I guess, like a pattern that can be built up. I don't know how. It's like magic. I'll talk about limitations in a second, but transmission is 2D. That's, I guess, the bad thing about it. But its best thing is that it, I think, 0.1 nanometers resolution. So a way better resolution, but it's 2D. And I think the way that works is, yes, it passes through the specimen. So if your specimen's there, it passes through. That's how it's able to get even the tiniest of details. Because remember, electrons are smaller than the wavelength of light, so we can see them more. Very crazy stuff. So the limitations of both of these are that obviously they're very expensive, but don't say that in an exam. It's the most generic thing ever. You won't get marks for it. You have to talk about how, for transmission, it's an incredibly complex staining process, I think involving silver. It's a very complex staining process, very tedious, having to prepare a sample. You can't do it with live specimens, which is obvious because a vacuum. It needs to be in a vacuum, the specimen. That's because air will mess up the electrons. If we assume these are like air here, it'll mess up the electrons. So it needs to be in a vacuum. So you can't do it with live things. So they need to be thin. It's a complex staining process. And the sample can actually be damaged because of the energy that the electrons release, the high amount of energy. So this leaves artifacts. But this is only for transmission. Because think about it. If we have little, I guess this is the specimen. If we have a bunch of electrons going through, it's going to leave artifacts. Not like the ones that Indiana Jones finds. I guess just visual distortions. You can find them in old photos too, like artifacts, like little like blotches. Or I guess things like AI. If you use AI images, you might find some of them. So the two differences between SEM and TEM, scanning is going to produce a 3D image, but it has a resolution of 20 nanometers, but transmission has a 0.1 nanometer resolution, so way better, but 2D images. Those are the main differences. So yeah, I'm very happy with that, guys. That's all of this stuff recently. Okay, the light tick cycle. We might do this. I don't know, actually. It's pretty easy to understand. Cells are freely permeable. Basically, viruses attach to the host cell. The RNA is entered. Reverse transcriptase is used if it's a specific type of virus. Synthesis of viral genomes and proteins. Assembly, the cell lyses. Let's actually go over the structure quickly. For viruses, you have a lipid envelope, attachment proteins, capsids, and genetic material. But bacteria have slime capsules, circular DNA, genetic material, a membrane, a murin cell wall, and pili, which allow the cells to join together to swap genetic information, swap plasmids. That's, I think, everything. So we've done cell biology. Now, me and Ellis are actually going to be working on the history document tonight for the America section. How fun. So I'm just going to quickly... I'll go add some information to that later. Self-fractionation. But for history, honestly, doing history is so difficult to revise for. I don't know. It's difficult to revise for. It's a lot of data, a lot of information. I mean, for the World War II topic, it's very generic, but that's because eventually you go and do a lot more difficult stuff. So yeah, that's basically it. That's all that I wanted to, I guess, do today. I mean, we could go over enzymes, but it's really basic. They're proteins that act, or basically are, like catalysts. They reduce the activation energy for, I guess, metabolic reactions on a cellular level. And they can do this by obviously reducing the activation energy so that it can work in the human body temperature. So yeah, that's basically that. So thank you guys for watching today's revision stream. Hopefully it was understood and hopefully it all made sense. We went through the microscope stuff, we went through self-fractionation, and we went through mitosis. Big bits of information to remember for this topic, well, for cell biology, is that you can always kind of link it in a way to other stuff. A bit like how in chemistry, or generally you can link certain stuff together. Not really much for this topic, but if you can find one point, you can branch off from it. So you can talk about how, I mean, you can just infer from the name scanning that, you know, it's going to scan, it's going to create a 3D image. Then you can think, alright, well, if the scanning does a 3D image, transmission's obviously going to do a 2D. Then you got to think, I mean, 3D is better than 2D, so I guess it needs to balance out. Transmission is going to have a higher resolution than scanning. Magnification is how much an image has been enlarged by, and resolution is just how clear an image is. And yeah, that's basically it, guys. So thank you for watching. Thank you for watching. I'm not going to end the stream, so this is going to loop for the next maybe 12 hours before it automatically ends. So I'll see you guys on the flip side. See you guys on the flip side.